As mathematicians attempted to solve problems using their own methods, some of them became popular within the circle of mathematicians and eventually were named after the person. Hi, my name is Jason Rosenberry, and one of the methods we will pursue in today's lesson is the Simpson rule, but let's start by looking at the trapezoid rule. Trapezoidal rule. To approximate, and keyword being approximate, to approximate the definite integral from a to b of f of x dx, we will use t equals h over 2 times the quantity y sub 0 plus 2 times y sub 1 plus 2 times y sub 2 up to plus 2 times y sub n minus 1 plus y sub n, where the closed interval a to b is partitioned into n subintervals of equal length, and that length h is equal to b minus a all divided by n. Let's try an example. Use the trapezoidal rule with n equals 4 to approximate the value of the integral. Use the concavity of the function to predict whether the approximation is an overestimate or an underestimate. Finally, find the integral's exact value to check your answer. So let's use the trapezoidal rule to approximate the definite integral from 0 to 4 of square root of x dx. So just to list some facts, our a value would be 0, b value would be 4. We're told in the problem that n is equal to 4, so therefore the width of each partition, h, or the width or height of each trapezoid, h is equal to b minus a, 4 minus 0, over n, which is 4, so our h value is 1. Now we can do our approximation using the trapezoidal rule. So using the following equation, we can now substitute t equals h over 2. Recall that h was equal to 1, so we have 1 over 2 times the quantity. Y sub 0 is our a value. So we want to figure out y sub 0, or what is the square root of x evaluated at x equals 0. So the square root of 0 is 0 plus 2 times y sub 1. So we're going to start at 0 and now go in increments of 1 until we get to 4. So this is plus 2 times the function evaluated at 1, square root of 1 is 1, plus 2 times square root of 2, plus 2 times the square root of 3, plus finally we evaluate our function at our b value, which is 4. The square root of 4 is 2. Now we do the arithmetic. So t is equal to 1/2 times 0 plus, here's 2 and another 2 make 4, plus 2 root 2 plus 2 root 3, and t is approximately equal to 5.146. Next, we want to consider the graph of our function, and recall that the graph of y equals the square root of x looks something like this. From 0 to 4 looks something like this. The concavity of this graph is what we're interested in. This graph is concave downward from 0 to 4, and since it's concave downward, this estimation will underestimate, so that means it's lower than the true actual value of that definite integral. The last step is let's actually find out what the value of that definite integral is. So let's evaluate the definite integral from 0 to 4 of square root of x dx. The antiderivative of square root of x is 2/3 x to the 3/2 power. And we want to evaluate that from 0 to 4. So we'll substitute 4 in first. So we'll have 2/3 times 4 to the 3 halves minus what we get when we substitute 0 in, but that is just 0. So we're left to evaluate 2/3 times 4 to the 3 halves, and that is 16/3. So as you can see, this value, which is our approximation, is less than, so it underestimates the true definite integral value of 16/3. Let's look at another approximation method called Simpson's Rule. Simpson's Rule. To approximate the definite integral from a to b of f of x dx, use s equals h over 3 times the quantity y sub 0 plus 4 times y sub 1 plus 2 times y sub 2 plus up through plus 4 times y sub n minus 1 plus y sub n, where the closed interval from a to b is partitioned into an even number of subintervals of equal length, and that length h is b minus a, that quantity all divided by n. So with the trapezoidal rule, you can use any number of n subintervals, whereas when using Simpson's rule, you must use an even number of subintervals. Let's try this rule out. Use Simpson's rule with n equals 4, notice that's an even number, to approximate the value of the integral. Find the integral's exact value to check your answer. So looking again, we have a equals 0, b is equal to 2, n is equal to 4, so we can find h, which is b minus a over 4, so our h value is 1/2. Now we can use Simpson's rule. So s equals, our h value is 1/2. So 1/2 divided by 3 is 1/6. Recall that our function is simply f of x is equal to x. So y sub 0 would equal, we're integrating from 0 to 2. So we want to evaluate function f at 0. So that is 0 plus 4 times our first jump. So we started 0, and remember we're going in increments of 1/2 now. H is 1/2. So we're going to go to our first jump, which is 1/2. So f of 1/2 is 1/2. Plus, notice the next coefficient is a 2. So now we have to jump another 1/2. So we were at 1/2. We're going to go another 1/2. So we're at 1. So f of 1 is 1 plus 4 times y sub 3. Our next jump would be another 1/2. So that would be 3/2. And finally, our last term, y sub 4, we're at our endpoint of 2. So f of 2 is 2. Now we need to do some arithmetic, and we see that s is equal to 2. Now let's go ahead and actually find the value of the definite integral to see how close our approximation is. So here's our definite integral from 0 to 2, x dx. The antiderivative would be x squared over 2, and we want to evaluate that from 0 to 2. Substituting 2 in, we get 4 squared over 2, which is 2. 2 squared, which is 4, that divided by 2 is 2. Minus what we get when we substitute 0. So that answer is 2. So here our approximation of 2 was in fact the true value of this definite integral. Now it's time for you to try a problem. Use Simpson's rule with n equals 4 to approximate the value of the integral. Then find the integral's exact value to check your answer. Pause the video while you work on this problem. When you are finished, restart the video to check your solution. So a is 0, b is 4, n is 4. Now we can find h. h equals b minus a over n, or 4 minus 0 over 4, which is 1. Now it's time for the approximation. So using our equation, s equals, we would have s equals, remember h was equal to 1, so that's 1/3 times y sub 0. Our lower limit of integration was 0, so f of 0 would be 0, plus 4 times y sub 1. Our h value is 1, so we're going to jump to f of 1, and the square root of 1 is 1, plus 2 times y sub 2. Our next value would be 2, so f of 2 would be the square root of 2, plus 4 times the square root of 3, plus our last term, which we would use another h value of 1, so we're going to plug 4 into the function, and the square root of 4 is 2. Now let's perform the arithmetic, and we will see that s is approximately equal to 5.2522. Let's compare this with the true value of that definite integral. So let's evaluate the definite integral from 0 to 4 of square root of x dx. This would be equal to the antiderivative 2/3 x to the 3/2 evaluated from 0 to 4. Substituting 4 in first, we would have 2/3 times 4 to the 3/2 minus what we get when we substitute 0 in, which is just 0. And evaluating this expression, we get 16/3. 16/3. So you can see that our approximation of 5.2522 is very close to the true value, which is 16/3. Each of these rules, both trapezoidal and Simpson's rule, is an approximation, so there is some error. Let's look at some formulas that will help us calculate the error in each case. Error bounds. If t and s represent the approximations to the definite integral from a to b f of x dx given by the trapezoidal rule and Simpson's rule respectively, then the errors, meaning the difference or the distance between the true value and our estimate, we're going to call those errors E sub t for the trapezoidal rule and E sub s for Simpson's rule, satisfy the following. The absolute value of E sub t will be less than or equal to b minus a over 12 times h squared times m sub f double prime. Over on the Simpson's rule side, the absolute value of E sub s will always be less than or equal to b minus a over 180 times h to the 4th times m sub 4th derivative of f. Where the closed interval from a to b is the interval of integration, h is the length of each subinterval, m sub f double prime is the maximum value of the absolute value of all function values coming from the second derivative on that interval a to b, and m sub f to the 4, or the 4th derivative of function f, is the maximum value of the absolute value of the 4th derivative, the largest value, function value of the 4th derivative function on that interval from a to b. Let's try an example. Consider the definite integral from -1 to 1 of sine x squared dx. Part A, find the second derivative of f for f of x equals sine x squared. Part B, graph y equals the second derivative of f in the viewing window -1 to 1 by -3 to 3. And Part C, explain why the graph in B suggests that the absolute value of the second derivative of f is less than or equal to 3 for x values between -1 and 1 inclusive. Part D, show that the error estimate for the trapezoidal rule in this case becomes absolute value of E sub t less than or equal to h squared over 2. Part E, show that the trapezoidal rule error will be less than or equal to 0.01 if h is less than or equal to 0.1. And finally, part F, how large must n be for h to be less than or equal to 0.1? Let's start with part A. We're asked to find the second derivative of function f, given that f is sine of x squared. So the first derivative would be cosine of x squared. Chain rule would kick in. We have to take the derivative of x squared, which would give us another factor of 2x. So the first derivative would be 2x cosine x squared. Now to find the second derivative, we'll use the product rule. So that would be first function, 2x, times derivative of the second function. So the derivative of cosine would be negative sine x squared times, again chain rule, times 2x plus second function cosine x squared times the derivative of the first function, which would just be times 2. So we'll simplify this, and our second derivative with respect to x would equal 2 cosine x squared minus 4x squared sine x squared. Part B to our problem says to graph the second derivative in the viewing window -1 to 1 by -3 to 3. So here we have the graph of our second derivative, f double prime of x equals 2 cosine x squared minus 4x squared sine x squared. And looking at the graph, we have the viewing window set up as described. We have the x-axis spanning from -1 to 1, and we have the y-axis spanning from +3 to -3. So the graph would be the values of our second derivative from -1 to 1. And as we can see, as we go from x equals -1 to x equals +1, all of the function values, all of the second derivative values are between, no matter what we pick, those function values are between -3 and +3. Actually, it's between +2. So as we say here, all second derivative function values are between -3 and +2 for x values between -1 and 1. So that implies that the function values are all within 3 spaces away from 0 on the y-axis. So that is saying that the absolute value of f double prime of x is less than or equal to 3. Part D is asking us to show that the trapezoidal error, the absolute value of that error, is less than or equal to h squared over 2. So here I have the formula, absolute value of e sub t, less than or equal to b minus a over 12 times h squared times m sub f double prime. So substituting those values in that we know that this would be less than or equal to b minus a. B is +1 minus a is -1. Remember, we were integrating from -1 to +1. All of that over 12 times h squared times m sub f double prime, which we found out by looking at the graph that value will always be less than or equal to 3. So m sub f double prime is equal to 3. Now we can simplify. This is less than or equal to our fraction. We have 1 minus -1, so it's 2 over 12. That's 1 over 6. 1 over 6 times h squared times 3. Again, one last simplification would equal h squared over 2, which is what we were asked to show. Part E, show that the trapezoidal rule error will be less than or equal to 0.01 if h is less than or equal to 0.1. So here's our error formula. The absolute value of e sub t will be less than or equal to h squared over 2. and we'll substitute 0.1 in for h. So that gives us less than or equal to 0.1 squared over 2, which equals 0.005. And we know that that is less than or equal to 0.01. So there we showed that if h is less than or equal to 0.1, then the error will be less than or equal to 0.01. Part F, how large must n be? N being the number of subdivisions. How large must n be for h to be less than or equal to 0.1? So we know that h is equal to b minus a divided by n. And we want h to be less than or equal to 0.1. So we'll set that equal to 0.1. Actually, we want b minus a over n to be less than or equal to 0.1. So solving that inequality, we know that the b minus a difference is 2. b minus a is 2, and that's over n, less than or equal to 0.1. And when we solve that inequality for n, that implies that n must be at least 20 subdivisions. So if we use an n value of 20 or more, then that would cause h to be less than or equal to 0.1, which causes the error to be less than or equal to 0.01. In this lesson, we explored the trapezoidal rule and Simpson's rule and applied both of them to problems. Be sure to work the exercises that your teacher assigns. We'll see you next time.